Hi, and welcome to the very first episode of Failurology, a podcast about engineering failures. I'm your host, Nicole, and I'm from Calgary, Alberta. I have over a decade of experience in the field of mechanical engineering and building science, directing the construction of plumbing, heating, ventilation, and air conditioning systems in various high rise, multifamily residential, and commercial buildings across Western Canada. I love reading about engineering failure case studies, not just the science behind what went wrong, but what we can learn as an engineering community to prevent future failures from happening. Starting a podcast has been a dream of mine for a long time, and I'm so excited that it's finally here. I want to thank each and every one of you for listening. I hope these stories interest you as much as they interest me. And if there's a failure you want me to cover on a future episode, or if you want to see pictures or links from this episode, check out the podcast webpage at failurology.ca. Before we get into this week's failure, I want to share a small piece of engineering news. The FSO Nabarima is a floating storage vessel filled with oil that has been abandoned in the Port of Paria between the island of Trinidad and the east coast of Venezuela since January 2019, almost 2 years. It's being held in place by 8 anchors and is currently tilting or listing 25 degrees due to faulty oil transfer valves displacing the oil inside to starboard. In addition, there are reports the generator room has flooded and most, if not all, of the electrical systems are compromised. The oil in the Nabarima was abandoned on its way to America when the U.S. government imposed sanctions against the Venezuelan state-owned oil company. The ship currently holds more than 1.3 million barrels of oil, 5 times more oil than the Exxon Valdez disaster in Alaska in 1989, which is still impacting the shoreline of the Prince William Sound today. Currently, nothing is in place in the Port of Paria to contain a spill. Even a minor spill would extend north into the Caribbean Sea, impacting the entire region for years to come. As of the end of October, there are allegedly plans to remove the oil from the Nabarima, but the ship Venezuela plans to use can only hold about 300,000 barrels and will need to make many trips to empty the Nabarima. Environmental scientists are monitoring the situation for a potential oil spill using satellite imagery and radar. On the podcast website at failurology.ca, there is a link to a National Geographic article if you want to read more about the FSO Nabarima. Now on to this week's engineering failure, the Citicorp building located in New York City. I chose this building for the first episode because no one was hurt. There was no catastrophic failure. The issues with the design were discovered before anyone was hurt. Engineers are not infallible and mistakes do happen, but how those mistakes are handled can make a big difference. Construction of the Citicorp building began in April 1974 and was completed in October 1976 for a cost of 195 million US dollars, which is equivalent to approximately 924 million today. The building officially opened 1 year later in the fall of 1977 once construction of the Citicorp offices was complete. It stands 59 stories tall at over 250 meters, and at the time of construction, it was the 7th tallest building in the world. It's currently the 21st tallest building in New York City. The development was a partnership between Boston Properties, a real estate investment trust, or REIT, who still owns the building today, and Citibank, the anchor tenant. William Lemessurier, principal of Lemessurier Consultants, was the structural engineer of record for the project, operating out of Cambridge, Massachusetts. Lemessurier worked with New York engineering partner, the Office of James Rudderman, to complete the Citicorp building project. For a building this size, it isn't uncommon for a design engineer to partner with a local engineering firm to assist in the workload and provide local code knowledge. The northwest corner of the Citicorp site in Midtown Manhattan has been occupied by the St. Peter's Lutheran Church since 1905. The church and Citicorp formed an agreement allowing the tower to be constructed as long as the church was rebuilt on the same corner. One of the stipulations of the agreement was that the church could not be connected to the tower in any way. Structurally, Lemessurier had to be creative to support the large tower without any of the structure carried from the northwest corner of the site. In order to accomplish this, his design used 4 large columns located on the center of each of the building faces, rather than at the corners, causing the corners of the building to cantilever 22 meters out from each of these 9-story columns. To account for the weight of the building and its occupants, as well as additional loads created by wind, the tower used an inverted chevron design, or large V-shaped structural members on each of the exterior faces of the building to offset the load from each floor down to the 4 central columns below. There are 6 chevrons that stack up each of the 4 building faces, 24 Vs in total, which are connected to additional support members at the slab. There are pictures of the central columns and chevrons on the podcast webpage if you want to take a look at those. In addition to the chevrons, the building design also contained an active tuned mass damper located in the penthouse. The damper, actuated by a motor, acts as a pendulum to counter building sway caused by wind. The damper installed in the Citicorp building is 410 tons, attached with springs, and floats on a bed of oil. It decreases building sway by up to 50%. Another interesting design feature, although unrelated to the failure, are the double-deck elevators, which have 2 cabs stacked one on top of the other, allowing passengers to access 2 floors simultaneously. Access between odd and even floors can be done using escalators throughout the building. Using double-deck elevators reduced the number of elevator shafts required and increased usable floor area and leasable space. As the head structural engineer and principal in charge, Lemessurier completed the design concept and overall structure, while the details of that design were completed by his engineering team and their New York firm partner. This isn't uncommon in everyday engineering practice. The design for a building this size is simply too large and complex for one person to complete alone, even if they weren't working on other projects. Assuming that the component design met or exceeded the design parameters provided by Lemessurier, the design engineer's detailed work may not be overseen directly. It's nearly impossible for one person to oversee every single component of a design. Although Lemessurier was probably involved in coordination and design discussions throughout the design and construction process. In 1974, the New York Building Code only required perpendicular wind load calculations, or loads where wind hit each building face head-on. The code did not require structural calculations for quartering loads when wind hit the corner of the building or 2 sides simultaneously. It was the 70s. Codes evolve and improve every year. This code shortfall was compounded by the fact that the structural design engineers on Lemessurier's team viewed the chevron members as trusses rather than columns, meaning that the chevrons or Vs were deemed to be exempt from and did not follow the safety factor requirements outlined by the American Institute of Steel Construction specifications. In May 1978, Lemessurier had learned in a meeting related to another project that the structural team for the Citicorp building allowed the contractor to use bolted connections in lieu of the specified welded connections where the individual chevron members were joined to the building structure at each slab. Bethlehem Steel, who was responsible for construction of the steel structure for the Citicorp building, had proposed the use of bolted connections, arguing that welded ones were not necessary and too expensive to make the project feasible. Between the perpendicular wind load calculations and erroneously treating the chevron members as trusses, it was believed at the time that the bolted connections met the design parameters. Boy, were they wrong. Lemessurier was not consulted on this change, and he learned about it for the first time in the May meeting. It seems a gross oversight to not inform the signing engineer of a change of this magnitude, but the engineering team likely didn't understand the significance of changing the connection type. It is very common for contractors to propose more cost-effective and often less stringent methods, materials, or equipment to meet the design engineer's intent. This is often referred to as value engineering. The engineering teams must thoroughly review each proposal and determine if it does in fact meet the requirements before it can be accepted. In the industry today, budgets and schedules are very tight. There's an ever-growing pressure on engineers to provide cheaper and simpler designs, but public safety must remain paramount. In addition to a collaborative value engineering process, there are also instances where a contractor changes the construction details without notifying the engineer, which stresses the need for engineering firms to review the installation of their design throughout construction. Although from what I've read, the alternate proposal to change from bolted to welded connections appeared to have been submitted and reviewed by the engineering team before it was installed. In June, nearly a year after the building opened, Lemessurier was contacted by Diane Hartley, a civil engineering student at Princeton University, and Joel Weinstein, a design engineer, questioning the integrity of the structural design with respect to quartering winds. Lemessurier reran his calculations and quickly realized there was a 40% increase in overall wind loads, translating to a 160% increase in load placed on the chevron bolted connections. This greatly exceeded the safety factor in the structural design. Based on this new information, Lemessurier calculated the building structure could fail in a 1 in 16-year storm, or that each year there was a 1 in 16 chance the building structure could fail. To double-check his calculations, Lemessurier contacted Alan Davenport, who at the time was the director of the Boundary Layer Wind Tunnel Laboratory at Western University in London, Ontario. Davenport ran wind tunnel tests of the building structure and ultimately confirmed Lemessurier's frightening suspicions. Lemessurier had to either face the embarrassment and liability of notifying Citicorp that there was a major flaw in the structural design, or hide this information and put the building, its occupants, and its neighbors at risk. Lemessurier briefly contemplated suicide, but in the end decided the best option was to notify Citicorp. On the last day of July 1978, Lemessurier met with his liability insurance, Northbrook Insurance Company, and their lawyers to discuss what he had learned. The lawyers were skeptical at first. They brought in another structural engineer, Leslie Robertson, who designed the twin towers of the World Trade Center completed in 72 and 73 to review the calculations and act as an expert advisor. Robertson had worked with the National Science Foundation and the National Research Council studying the aftermath of earthquakes, floods, and hurricanes, and later he would review the World Trade Center following the 1993 bombing and 9/11. 2 days after meeting with the insurer, Lemessurier had the green light to alert Citicorp. He met with then Citicorp VP John S. Reed, who is now the chairman. Upon realization of the magnitude of what Lemessurier told him, Reed brought Citicorp chairman Walter Wriston up to speed on the issue. After several hours of frank discussion, Citicorp agreed to proceed with the repairs as quickly as possible. Although Lemessurier provided design and safety recommendations, Robertson was retained as a third-party consultant to oversee the redesign, repairs, and safety measures put in place. In the days that followed, Citicorp drew up several contracts. Bethlehem Steel, the original steel constructor, was no longer in the business of steel skyscrapers, so Carl Koch Erecting, who constructed the steel structure for the World Trade Center complex, was brought in to complete the Citicorp repairs. In case you're wondering, I haven't been able to confirm one way or another if Carl Koch is related to the Koch brothers. Also, emergency generators were installed immediately in the Citicorp building, and MTS Systems Corporation in Minneapolis was engaged to provide round-the-clock technical support to keep the active tuned mass damper they had supplied operational. A California company was also hired to install strain gauges on structural members, which would monitor every movement of the building until the repairs can be completed. An interesting tidbit, the California company did not hire union electricians to install the gauges. It's been said that someone snuck into the building one night and snipped the wires on the gauges. This initially caused some confusion, but was quickly corrected. And lastly, weather experts from Brookhaven National Laboratory on Long Island provided weather predictions 4 times a day. A week after sounding the alarm on the shortcomings of the structure, Lemessurier's design drawings for the repairs were issued. The repairs required 50 mm by 1 meter long steel plates welded across each of the over 200 bolted connections. HRH Construction, the original general contractor for the building, would oversee and manage the repair work, which included Carl Koch Erecting, laborers, drywallers, etc. Citicorp issued a vague press release mentioning that additional welding would take place to stiffen the building structure and assured the public that there was no danger. The day after the press release was the start of New York City's paper strike related to press room staff reductions. 7 days a week for the next 3 months, carpenters and drywallers worked from 5 p.m. to 8 p.m. every night removing drywall, allowing access to the existing bolted connections, and installed hoarding enclosures to protect the existing offices. Welders worked every night from 8 p.m. to 4 a.m. welding on the new steel plates. 6 weeks after repairs started and were about halfway complete, Hurricane Ella was on a course to hit New York. An evacuation plan was prepared, and the American Red Cross was ready to provide disaster relief if required. Luckily, the hurricane diverted east before hitting the city, sparing the building from disaster. The repairs were finally completed in October without any more major storm events. New calculations for the building estimate that it could withstand a 1 in 700-year storm. Coincidentally, due to the timing of the paper strike, which ended a few weeks after the structural repairs were completed, the repairs were mostly hidden from the general public until a New Yorker article was published in 1995. The article is called The 59-Story Crisis, written by Joe Morgenstern, and I highly recommend reading it. The exact cost of the repairs is unknown, as Citicorp did not disclose this information. However, HRH Construction estimates a cost of $8 million US. Following the completion of the repairs, Lemessurier was served a claim from Citicorp for $4.3 million. However, Northbrook and Citicorp eventually came to an agreement that Northbrook Insurance would pay Citicorp $2 million, or Lemessurier's limit of liability. LeMessurier was hailed a hero by all for his candor and courage. Expecting his insurance rates to increase, Northbrook felt he acted quickly and ethically, and as a result, lowered his premium. Citicorp sold 2/3 of their interest in the building in 1987 to a Japanese company for $670 million, and they sold their controlling stake to the building to Boston Properties in 2001 for $755 million. The building was renamed 601 Lexington Ave in 2009. LeMessurier sadly passed away in 2007 due to complications following surgery after a fall. He was 81 at the time. In addition to the Citicorp building, he also designed structures for the Boston City Hall, the Federal Reserve Bank of Boston, the Singapore Treasury Building, and the Dallas Main Center. Over the course of his career, he's received many achievements, several of which were given after the Citicorp near miss. In closing, I want to leave you with an important message from LeMessurier written in the New Yorker article. You have a social obligation. In return for getting a license and being regarded with respect, you're supposed to be self-sacrificing and look beyond the interest of yourself and your client to society as a whole. And the most wonderful part of my story is that when I did, nothing bad happened. My sources for this episode are Wikipedia, the 59-story crisis article from the New Yorker published in 1995 and written by Joe Morgenstern, and the Canadian Professional Engineering and Geoscience Practice and Ethics textbook written by Gordon C. Andrews. One document I saw referenced several times but was unable to find was LeMessurier's report detailing the design flaws called Project Serene, the special engineering review of events nobody expected. If anyone knows where I can find a copy of Project Serene, please let me know. I would love to read it. Please check out the podcast webpage at failurology.ca for photos and links from this week's episode. Drop a comment and let me know if there are any engineering failures you want me to cover, and thanks again to everyone for listening. Tune in next week as I tell you about the levee failures in New Orleans during Hurricane Katrina. Bye everyone. Talk soon.